SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 24. In last lecture we have started discussing different flow track configurations, and we can say this is also a part of aerodynamic design of axial flow compressor. We were discussing about different flow tracks. We can say we can have constant tip diameter flow track, we can have constant hub diameter flow track, we can have constant mean diameter flow track, we can have combination of constant tip and hub kind of configuration. And we realize, like, once we are decided with say total pressure ratio required by say LP compressor or HP compressor, we need to decide with number of stages. Once we decide with the number of stages, systematically we need to do our calculation for per stage pressure rise. And for that, at the initial stage we will be configuring with some tracks, maybe say constant tip track, maybe constant hub track, or maybe say constant mean track. So once we are deciding with that track configuration, systematically we will do all our calculation at the exit of the stage, and then after we will be smoothing out that track. Let's recall what all we have discussed in the last session. So if we look at say constant tip kind of configuration, we realize at the initial stage, because we are having say constant tip configuration, we can achieve per stage pressure rise to be large. That means in order to achieve particular pressure ratio using number of stages, then the number of stages required will be lower. If that's what is your case, that's what will be reducing the length of your engine. But at the same time, in the later stage, when we are moving on the rear side, my blade height that will be going to be reduced. If that's what is your case, that will lead to increase of your secondary losses, and we can say that's what will lead to reduce in the efficiency. If we are having say shorter blade, it will be having very high stress, that is giving mechanical constraint. And if we are using this kind of configuration, we can say we are having drag to be very high. Okay, and it uses the maximum size of the engine. That's what is available with that. That's what is, we can say it's a constant tip kind of configuration. Now in order to mitigate what we have limitations in sense of last stage height of the blade, we are moving with say constant hub kind of configuration. Now in constant hub configuration, if we look at our radius, or we can say our diameter at the tip, that's what is going to reduce. That means my per stage pressure rise, that's what is going to reduce. So in order to achieve the required pressure ratio, you may need to go with say more number of stages. But at the same time, because this is what is having tapering shape, that's what is giving benefit in sense of reduction of your drag. And what limitation we have in sense of losses and in sense of efficiency, that's what we can mitigate by going with constant hub diameter configuration. And we were discussing mostly for your high bypass ratio engines, HP spool, that's what has been designed with this kind of configurations. Then we were discussing about the constant mean diameter configuration. If we go with constant mean diameter, that's what is, it says you are having per stage pressure rise you can get to be more. Under that configuration, if we go, we are having the shape of our track that's what is tapered shape, that's what is going to reduce your drag. Okay, and in order to address the problem with the height of the blade, maybe in the later stages or in the rear stages, we can adjust our shape of this track. So that's what is the flexibility we have with constant mean diameter. And this is what we can say we can use mostly for our medium size engines. Okay, and later we have discussed about the constant tip and hub diameter kind of configuration, and what we realize, what all problems we have, say we are able to achieve high pressure ratio with earlier stages. The problem with my blade height, that can be rectified by using constant hub diameter kind of configuration. So this is what is helping in sense of reducing our drag. So mostly for 2 spool and 3 spool configuration, this kind of flow track, that's what is most preferred. Okay, now this is what is giving us initial background for having our track. Now let's move towards what exactly we are looking for. That's what is called compressor cascade. Now cascade, that's what is need to be understood thoroughly. What exactly is the meaning of cascade? Suppose if I consider this is what is, say, my rotor, and we know this rotor throughout my span, it is comprising of number of aerofoils. Suppose if I consider, say, 5%, 50%, 95% of my span, if I look at these, all aerofoils are of different kinds. So let me show you here. So here if you look at, this is what is my profile at 5% span. So you can say when we are looking at our delta beta, that's what is giving me this kind of curvature. This aerofoil, it is a indigenous aerofoil, it is individual aerofoil. If I am going here with the 50% span, you can understand when we are moving away from my hub, my radius, that's what is going to increase. And let me introduce the parameter what earlier also we have discussed, that's what is called pitch. So pitch of this blade, that's what is defined as 2 pi r divided by z. So distance between these two blades, if you look at, that's what is called the pitch of my blade. Okay, and if you consider here, this is what is my pitch of cascade. If I am moving at 95% span, we will be having this kind of configuration. So here what arrow, that's what is showing, it says this is what is my flow direction. Okay, now this aerofoils, if you look at particular station, they are arranged in a linear manner, and that is the reason why this is what is called linear cascade. Or you can say, suppose if I'll be having this as one of the circle, I'll be opening that circle and put it on plain wall or say plain paper. So if we are putting like that, we will be having this kind of arrangement. That's what is called linear cascade. Okay, now at all stations we are having different aerofoils. At all stations we are having different delta beta. Okay, so in order to select the aerofoil at particular station, we need to have a data. What data we are looking for is what will be my CP. CP is nothing but that's what is representing, say, pressurizing capacity for particular aerofoil when we are talking about application to, say, axial flow compressor. So what we will be doing, we will be arranging our blades in this manner. So here if you look at, these are two blades, that's what is called instrumental blade. And if you recall, I was showing you the cascade blade in which at different spans, say suppose if you consider this is what is near, say, my one wall, I am having pressure tappings. Say here at the mid station I am having pressure tapping, near the other wall I am having pressure tappings. So similar kind of tappings we are having on pressure surface as well as on suction surface. So when we will be fixing this test blades, these blades, and this is what is my test section in tunnel, that tunnel it is called linear cascade tunnel. and that's what will be giving us idea about what is happening with my CP distribution. Now if I consider my flow, that's what is entering at particular angle. Suppose I want to check if I'll be changing the angle at which my flow is striking on this blade, that also can be done, and that's what will be giving us idea when my aerofoils are working under off design condition, what all will be the changes. Okay, so just realize this is what is my linear cascade. So during say initial stage of development of axial flow compressors and axial flow turbines, people they have done whole lot of experimentation with different kinds of aerofoils. Some of them we have already discussed. They are say subsonic aerofoils, transonic aerofoils. Say we have discussed about C4 aerofoil, we have discussed about NACA aerofoil, we have discussed about CDA aerofoil, we have discussed about DC aerofoil. All those aerofoils, they are being developed. They are being developed for particular pressure rise, for having particular kind of CP distribution. So this all data, they are of great importance. So systematically people they are doing experimentation, they are making the bulk of data for particular kind of aerofoils with different angle configuration, and they are having whole lot of data with all different kind of aerofoils. As and when required, they are recollecting those data, and those aerofoils they are being incorporated in particular blade for particular engine development. Okay, that's what is the importance of this cascade and cascade data. Okay, let me show you here. So if we consider, say this is what we can say as one of the aerofoil, we can say it is a cambered aerofoil, because you know it is not symmetrical but it is cambered one. So you can say this is what is my camber line. Okay, at particular station I am having my thickness to be maximum. This is what is my location where my thickness is maximum, and here if you look at, this is what I am defining as a chord of my aerofoil. Now if you recall, the upper surface what we are defining as my suction surface, a lower surface that's what we are defining as pressure surface. Now you know, based on understanding, based on the experimental data, people they have come up with different numerical schemes. They are having different equations for pressure surface, they are having different equations for the suction surface, and based on that new kind of aerofoils people they are developing. Okay, so initial start, that's what is working with already standardly available aerofoils, and later on they are modifying as per the requirement. So let's try to understand what all is our cascade. Okay, so here if you look at, these are two blades. Okay, you can say two cascades, they are being arranged in a linear manner. If I consider, this is what we can say as my camber line, that's what is dividing my blade in two equal halves. You can say the distance between my leading edge and trailing edge, that's what we are defining as chord. If I am measuring my vertical distance here in axial direction, that's what is called axial chord. So remember, the chord and axial chord, they both are different things. Okay, so this B we can say it is my axial chord. Now if you look at, if I am measuring my distance near leading edge from one point to next coming point, and that's what we are defining as a pitch, or we can say that's what is nothing but 2 pi r by z. So if you consider near the hub, my pitch will be smaller, my S will be smaller. Near my tip region we will be having our S to be larger, because it is 2 pi r by z. Okay, so my radius, that's what is changing, that means my pitch it is changing. Now if I consider, say this is what is my axial direction. Okay, you just remember this part. Again and again we are saying we are measuring all our angle with reference to axial direction. So we can say this is what is my axial direction. My flow, that's what is, say this is what is angle, we can say it is a blade inlet angle. I say this as alpha 1 dash and beta 1 dash. Do not get confused here. So people, when they are using this cascade data or when they are doing analysis for cascade data, if that cascade is of say stator, they are putting that as alpha. If this cascade is of rotor, they are putting that as a beta. Okay, so do not get confused here. So it is written separately. If we are considering as a stator, then I am putting alpha. If we are considering for the rotor, we are considering that as a beta. So you can say this is what is my blade inlet angle. Okay, now here at the exit, if you look at, this is what is my angle at the exit. That's what I am defining as a blade outlet angle beta 2 dash. Okay, now if I'll be drawing my tangent from say leading edge and tangent to my camber line, and from here from trailing edge to tangent of my camber line, what angle we are getting, that angle is defined as a camber angle. This is what is very important. This is what we say as a camber angle. Okay, so this is what is my camber angle. Now, we are setting this aerofoil in respect with the axial direction. So here if I'll be joining a line from leading edge to the trailing edge, and what angle it is making, that angle is defined as a stagger angle. Okay, so this is what is my stagger angle. Now if you look at what will happen, suppose if I consider my flow, that's what is incident on my aerofoil or on my cascade at certain angle, say alpha 1 or beta 1. Okay, do not forget this alpha 1 dash and beta 1 dash, that's what is my blade inlet angle, and the alpha 1 and beta 1, that's what we are defining as a air inlet angle. Okay, this is what is my air inlet angle. So what we mean here is, my blade, it is been designed for particular beta 1 dash or alpha 1 dash. In spite of that, my flow, that's what will be entering at angle other than this alpha 1 dash and beta 1 dash. And the difference of these two, that's what is defined as an incidence angle. This is what is an incidence angle. So, if we are looking carefully, if I am putting say alpha 1 minus alpha 1 dash or maybe beta 1 and beta 1 dash, that's what is defined as incidence angle. Remember, this kind of logic you have studied for your wings also in aerodynamics. There we are defining that as angle of attack. But for our case, when we are discussing about say our turbo machinery for axial flow machines or for radial machines, we are not writing that as a angle of attack. We are considering that as incidence angle. So do not get confused with angle of attack and incidence angle. Now here if you look at, this is what is representing my blade, and as we have discussed, this is what is velocity with which my flow is striking on my blade. Okay, what will happen? We know, since my aerofoil, this aerofoil, it is working under adverse pressure gradient, we will be having say flow separation that may be happening on the suction surface, or we can say there is a presence of low momentum fluid on my pressure surface, presence of low momentum fluid on my suction surface and pressure surface. So if this is what is your case, if you look at my exit velocity need to be uniform. In spite of that, I will be getting this kind of deficit. That deficit is nothing but that's what is called wake. Okay, so in actual case what will happen, it may be possible or it is required to come out with angle alpha 2 dash and beta 2 dash. In spite of that, my flow will be coming out with some angle other than that of alpha 2 dash and beta 2 dash. That's what is say alpha 2 and beta 2. Okay, and difference of this, that's what is called deviation angle. That's what is called deviation angle. So this is what is very important for us when we are doing our design for axial flow machines. Okay, so incidence angle, deviation angle, that's what will be coming into the picture during our design, initial stage of design. We literally need to sit down and we need to do the calculation of incidence angle and deviation angle. So whole this week what we have defined, we will be dedicating that for say cascade mechanics. Okay, or say we can say that's what is on cascade study. Okay, now like we have introduced now new angles other than alpha, beta. We are now introduced with say angle theta. That's what we have defined as a camber angle. We have introduced angle zeta, that is nothing but that's what is my stagger angle. We have introduced angle, that's what is my incidence angle. We have introduced new angle, that's what is my deviation angle. Okay, so we will be discussing in detail for all these aspects. Now coming again, so like the question is, what all are the uses of our cascade tunnels? So here if you look at, this is what is cascade tunnel, linear cascade tunnel, that's what is available at IIT Kanpur. And here if you look at, we can put our blades between these two test sections. Okay, and we will be having the measurements of inlet angle, measurement of outlet angle, what will be the distribution of CP, all those things, that's what we can measure. Okay, downside if you look at, that is what is say NTUA linear cascade tunnel. Compared to this cascade tunnel, the size of test section, that's what is larger. Okay, so we will be realizing what all are the importance of having larger size. But you can realize here, say for low speed testing, these cascade tunnels are of great importance. Okay, so what it says, that's what is say it provides several advantages such as geometrical simplicity, because my aerofoil, it is say same aerofoil, that's what we are extruding for particular span. You can have simple adjustment. Here if you look at, we are having the knob. By tilting that knob, we are able to change the angle of incidence to my cascade. Okay, and you can say we can go with the large blade sections. So here if you look at, this is what is providing the large blade section. Now let me tell you, as we have discussed, on the suction surface of my compressor blade, we are having all three flow phenomena, that's what is happening, means laminar flow, transition flow and turbulent flow. Now in order to have systematic study of that kind of flow, where exactly your transition is happening, how my flow is behaving on suction surface, you can imagine the size of my blade required, that will be larger. Then only we can go with the detailed measurement of each phenomena happening on the surface. Okay, so we can say by using this linear cascade, we can provide the quasi three-dimensional blade to blade data. Now many code development companies, they are looking for validation of those codes, and they are looking for dedicated data, that's what is available from cascade tunnels. So this is what is providing the helping hand to them. Okay, so this is what is also been helpful in order to understand what is happening in sense of flow physics within the passage. Okay, since we are having the larger scale of tunnel, we are able to do systematic measurement by available instrumentation, that is benefit. Here if you look at, say this is what is required, low capacity blower, but at the same time if my size of this tunnel, that's what is, or test section, that's what is increasing, my blower capacity or compressor required capacity, that also will be increasing, and it will be an expensive affair. I will show you. This linear cascade, that's also been used for studying the secondary flow field. So those who already have done the course on aerodynamics of turbo machinery, they will understand that part. Since this is what is beyond the scope, but you can understand secondary flow is nothing but that's what lead to losses. And when we are having this kind of flow, that's what is happening between the passage, that will lead to increase the losses and decreases the efficiency. So the thing is, we will be studying what is happening in sense of secondary flow, and we will try to mitigate that by having systematic design of these aerofoils. That is also a kind of study we can go with. Now here if you look at, say we are having subsonic aerofoils, we can test by using subsonic cascade tunnels. In line to that, we are having, say, transonic. So this is what is a trisonic tunnel, that's what is available at NAL Bangalore. And here if you look at, these are the aerofoils, that's what they are testing. So they are transonic aerofoils, they are testing there. Okay, this is what is one of the cascade tunnel, linear cascade tunnel available at DLR for transonic aerofoils testing. This is what is a recent development at Munich, and you can understand this is what is required, large capacity of my flow, it is required large capacity of my pressure ratio. So they have used a 3-stage axial flow compressor for this testing. Okay. Now the problem with this linear cascade tunnel, or we can say the limitation, is we are not considering the effect of variation of my static pressure along the span. So you can say my radial pressure gradient, that's what is we are omitting here, and that's the reason why many times this data that cannot straightway be applicable for the blades. Let me tell you, it is straightway applicable for aerofoil, particular section of aerofoil, not exactly applicable for blade. Blade and aerofoil, that you must understand, they both the things are different in that sense. Now these are some of the application as we have discussed for linear cascade tunnel. We can say we can study what is the variation of CP with the change of incidence angle, because that's what is very important. Suppose if I am selecting particular aerofoil and that aerofoil I am putting at some station in my blade. So what will be the effect of change of incidence? That's what is very important. So based on the available data, people they are selecting particular kind of aerofoil. Okay, we can analyze what is happening in sense of my secondary flow structure. Here we are neglecting the radial pressure gradient. We can examine the different kinds of loss generation. It may be, say, profile loss, tip leakage loss, end wall loss, secondary losses. So this loss mechanism also can be understood and studied by using this linear cascade tunnel. Now in order to study the effect of change of different geometrical parameter, very soon we will be discussing about this. Okay, so what will be the change? So you can realize, if I will be making my rotor of different configurations and if I will be doing my testing, it will be very expensive affair. Rather, in order to have quick solution or estimation, people they are studying this variation of geometrical parameters like stagger angle, solidity change, leading edge modification, end wall contouring. Those all things can be done by using this linear cascade tunnel. Okay, we can also investigate the effect of inflow parameters like change of Reynolds number, maybe free stream turbulence, inlet Mach number, upstream wake effect. All those things, that's what is affecting my performance of axial flow compressor. So before making design, people they are doing all this kind of study by using linear cascade tunnel. This linear cascade tunnel equally we can use even for turbine. So for cooling study, end wall cooling, you can use this cascade tunnel. This is people they have started exploring, say, aeromechanical or aeroelastic study using this cascade tunnels. So this is what is all with the linear cascade tunnel. So books they are discussing about the linear cascade tunnel, but in limited edition, since this is what is a dedicated course, though it is for design, but this is what is very important as a designer, how you will be using this data and from where this data is coming. That's what need to be realized and understood by you. Okay. Now there is a other possibility people they are moving with, that's what is called annular cascade tunnel. So you can say we will be making full scale. So here if you look at, this is what is the KTH annular cascade tunnel. Okay, so you can make all your blades, you can make your whole passage, and you can do the simulation or you can do the experimentation for that. But just realize, when we are moving, suppose say if I am doing my testing for say LP compressor, you can realize the number of blades for those LP compressors are more, diameter is more, and in order to do this say the testing, we need to have a whole lot of power. That's what is required, and that's what is one of the limitation. Now in order to address this limitation, people will say just reduce the size or do scaling of your blade. When I will be doing the scaling of the blade, the measuring instruments also need to be reduced in the size, because if I will be using say larger dimension instrumentation, that's what will be having blockage effect, that's what will not give what we are expecting. So this is what is the people they are using for aeroelastic study. People they have used this for say annular tunnel for say heat transfer study. So this is what is the flow visualization, what they are doing, what is happening near the tip region. Now here if you look at say, this is what are the blades, what we were discussing about say tandem bladed axial flow compressor, where we have discussed we are having our blade, that's what is a three-dimensional blade. Now if this is what is a three-dimensional blade, and if we want to realize, we want to analyze what is happening with my flow physics, we need to go for the testing, and for that testing I cannot go with the linear cascade tunnel. I literally need to go with say annular cascade tunnel. When I say we are going with the annular cascade tunnel, we have discussed based on my power requirement, based on my dimensions, we are having a whole lot of limitations. So in order to avoid that kind of situation, people they found with the solution, that's what is called sector annular cascade tunnel. Okay, in which we will be having say limited number of blades, that's what we will be testing with. Okay, and the working condition, that's what will be in line to what we are expecting. The flexibility here is we can do geometrical scaling. If we are looking for detailed flow physics, we can increase or decrease the size or height of the blade, or maybe aspect ratio of the blade, and we can do testing for that. Such sector annular cascade tunnel, that's what is been available at IIT Kanpur. So this is what is a sector annular cascade tunnel, that's what is available at IIT Kanpur. And the beauty of this setup, that's what is we are able to do our testing at equivalent to engine Reynolds number and equivalent to engine Mach number. So presently what nozzle we are having, say at the exit of nozzle we are able to achieve Mach 0.6. Okay, and if we want to go with say slightly higher Mach number or say lower Mach number as per the expectation, we need to replace this nozzle with the new nozzle, and that's what will serve the purpose. So now this is what is giving us flexibility to study all three-dimensionality effect. Okay, so this kind of facility, that's what is unique facilities. Okay, so similar to this at KTH, they are having their facility in order to do testing for HP turbine, and this is what is their sector annular cascade tunnel. Okay, now when we say what are the applications of this annular or sector annular cascade tunnel, we are looking for three-dimensional effects. When we say we are looking for three-dimensional effect, we are looking for what is happening with say application of pressure gradient. Okay, so we can have study of effect of change of geometrical parameter. As I was saying, these days people they are making blades, compressor blades, turbine blades of funny looking. They are having highly three-dimensional shape. In order to do that kind of testing, this is a tunnel we can use. We can say we can study a stacking definition, effect of lean and sweep. We will discuss all these things. Leading edge contouring, axisymmetric or non-axisymmetric end wall contouring. So where we are looking for the flow three-dimensionality, we want to study experimentally. That time we are using annular tunnel or sector annular cascade tunnel. So we can investigate what is flow interaction, what is the effect of upcoming wake from the rotor to the stator that we can go with. We can study the tip shape modification. Okay, we can go with the cooling study. We can also do aeromechanical study. So in overall, if we look at this, cascade tunnels are of great importance. So let's say what all we have discussed in this lecture. We have started with configuring what we say as a cascade or compressor cascade, and we have introduced new flow angles which we say as a camber angle, stagger angle, incidence angle and deviation angle. Then we started discussing about say linear cascade tunnel. We started discussing about say annular cascade tunnel, sector annular cascade tunnel, what all are the applications of these tunnels, okay, and how this data that will be used for our purpose. That's what we will be discussing in next lecture. So thank you very much for your kind attention.